Hi, this is Jay McClellan. This video is part 2 of my Build a Drone video series. In part 1, I went through all the components and did some numerical modeling to help select the best components to optimize the performance. And in this video, I'm going to take all of those parts and put them together and make a drone. So I'll be starting with this basic airframe kit, and we'll put all the pieces on and make it fly. I'll be using this F330 airframe kit, and if we look at the battery, there are 3 obvious options for where to put it. I can mount it on top, I can put it in the middle, or I could mount it on the bottom. I don't want to put it on the bottom in my case because I want to reserve this bottom space for payload. That leaves inside or on the top, and either one would be okay. I am going to put my battery inside the frame because I want to shift the center of gravity as low as possible. That'll help make it more stable. To mount the battery inside the frame is relatively straightforward, except for one minor problem. It doesn't fit. So I'm going to shave these down just a little bit in order to make room for the battery. So I took about 1.5 millimeters off of each inside leg, and now the battery fits in just perfectly. The bottom plate of the frame is designed to act as a power distribution board, where you could solder the battery connections here and then have 2 connections for each motor. But I don't want to have it like this, which is the bottom of the craft, because these open connections would interfere with the payloads I have in mind. And I don't want to flip this over and do the same thing inside, because then it would interfere with the battery. So I'm not going to use this for power distribution. I'm just going to use this as a physical bottom plate, and that'll give me a lot more options when it comes time to mount payloads on the craft. You don't have to mount the flight controller exactly in the center of the craft. It'll work if it's offset a little bit, but I'm going to mount it right in the middle. And I'm going to set it up on some spacers so that the receiver can be mostly tucked right underneath it. I'm going to mount the flight controller on these 12 millimeter nylon standoffs. That'll give me just enough room to slide the receiver underneath. Here's the flight controller sitting on the standoffs. Some people use vibration isolators at this point so that the vibration from the motors doesn't affect the flight controller as much. That's more of a problem in flight controllers that have more sophisticated features like an inertial-based position hold, where that vibration can throw it off. And with the simple flight controller like the CC3D, I find it works just fine on a fixed mounting system like this. I determined where I want the receiver to sit, and so I'm going to stick it down with a little piece of double-sided tape. Really, once everything's assembled, it won't be able to move significantly at all. So the tape isn't so much to keep it from falling out as just to prevent vibration. The connections going between the flight controller and the receiver are plus and minus 5 volt power supply connection, and then 1 connection for each of the receiver's channels. This is a 6-channel receiver. I have the legs attached, screws tightened down, and I put the battery back in just to make sure I still have a nice loose fit, and everything looks good. I attached a motor temporarily, and I temporarily attached the electronic speed controller with some twist ties to put it in the position where I want it. I'm going to make my power connections on the sides here, and so the power leads to the ESCs are already just the length I want them, so that works out great. The leads running to the motor, though, have way too much wire, especially on the motor side, so I'm going to have to trim these to length. And I like to use these little gold bullet connectors on the ESC to motor connections. A lot of people do, and because it gives a nice in-field disconnect, reconnect, so if you had to swap a motor, it's quite simple to do it. This assembled connector is 18 millimeters long, and the solder cups in each end extend inward about 2 millimeters, so this is going to add about 16 millimeters to the length of the wire. So I'm going to cut these wires and leave a 16 millimeter gap in between. Now I need to strip about 2 millimeters, maybe a little bit more, of insulation off the end of each wire and solder on the bullet connectors. I soldered all the connectors onto the wires and made sure I don't have any sharp protrusions of solder around the edges, so now it's time to insulate them. I cut lengths of 1/8 inch or 3 millimeter heat shrink tubing, and you want to get the end of the tubing a little bit beyond the cylindrical portion of the connector so that it shrinks down into this little narrowing neck just a little bit. That way when the barrel slides over this male connector, it'll make a solid connection with no exposed metal. I hold the tubing right where I want it and then start to shrink. And you could use a heat gun, but my preferred way to shrink it is to use a hot air rework station made for surface mount device soldering. I turn it down to about 150 degrees C and low airflow, and that lets me shrink it very precisely in a controlled way and without burning my fingers. To insulate the female connectors on the ESC, you want it to protrude a bit beyond the end of the tube. To finish off the female connectors on the electronic speed controls, I cut off the heat shrink tubing just a little beyond the end of the metal tube, so I have no exposed metal. Next, I'll attach the motors to the frame. So you're looking down at the top of the quadcopter with this being the front and this being the back. Motors on opposite corners diagonally must turn in the same direction. And the usual convention is for the front right propeller to turn clockwise, front left propeller to turn counterclockwise. That means this is a clockwise motor, this is a counterclockwise motor. But here's the trick. These motors are specified based on fixed wing aircraft, because that's where this type of motor started out. So as you view from the back of the motor, this motor is going to turn clockwise, but when you view it from above, its rotation actually is counterclockwise. Before attaching the motors, make certain that the screws you have are long enough to pass through the frame and thread fully into the base of the motor, but not any farther than that. If they go in too far, they'll hit the copper windings inside and short them out, and that will wreck the motor, and it will probably also wreck the speed controller. I have all 4 motors secured with screws, so now it's time to mount the speed controllers. And I'm going to mount the speed controllers with these large output transistors facing up where they'll get the best cooling. I'm going to connect the bullet connectors just in the order that's the least tangled at this point. We may need to swap some of them later on to get the motors to go in the correct direction, and that's okay. Sometimes these bullet connectors are really tight the first time you push them together, but after you've connected them once and pull them apart, then the second time it gets quite a bit easier. So next it's time to make the power connections, and I'm going to have power connections on each side of the quadcopter. So for each pair of speed controllers, I'll have a pair of red and black power wires coming up. And so I'll need to make a connection to each one, and then I'll join the power leads at the back where they connect to the battery. The XT60 connector has polarity markings on the side, and obviously you want to pay close attention to those. And I'm going to tin the solder cups so that they have solder in them before I try to put the wires in. And then while the connector is still pretty hot, I'll go ahead and get the wires set in and soldered in place. I've got good solid connections, so now I'll insulate them with some heat shrink tubing. My quadcopter power connector splits into 2 lines, plus and minus on each side. To make the power connections on this side, I need to solder together bundles of 4 wires. And the trick I use is to slide one of these crimp ferrules over the wires. These are really made to crimp on the end of a wire that you're going to put into a screw terminal. But I find them really useful for making solder joints like this. And all it really does is just hold everything together while I'm making the solder joint. And you want the ends of the wires exposed a little bit on each edge so you can get the solder to wet into the tube nice and cleanly. The power supply wiring is finished on the left side of the drone. I have my 2 16-gauge power lines coming in from the battery, and those split off into 20-gauge lines going to the 2 speed controllers, and then I also have a 22-gauge wire going down and under to supply power to the radio and the flight controls, and also to the payload bay. And the battery runs at about 12 volts, which is too high for the electronics, so I have this little battery eliminator circuit or voltage regulator that provides 5 volts at up to 1 amp to supply the flight controller and the receiver. The battery lines also split off here and go down to the payload section to provide power for payload such as camera gimbals. Each electronic speed controller has a twisted pair of black and white wires that provide the signal input to control the speed of its corresponding motor, and those run into the central section and connect to the flight controller. And I numbered these according to the convention of the software I'm going to be using, so you're looking down at the top of the drone with this being the back, and so they're numbered 1, 2, 3, and 4. and I put corresponding marks on the connectors as they come in so I can tell which is which and put them in order. This row of header pins on the back of the flight controller provides outputs to drive the speed controller. So I have the 4 speed controllers connected to channels 1, 2, 3, and 4. And then it has 2 additional channels, 5 and 6, that aren't used for flight. So I'm using those to send down to the payload bay in order to control things like a camera gimbal. And then I'm also feeding in my 5-volt power supply on the ground and 5-volt pins of one of these header sections. So that's what powers the flight controller, and it also powers the receiver through the cable that goes between the flight controller and the receiver. Coming out the right-hand side of the drone, I made this expansion connector to go to the payload bay, and I have battery plus and minus terminals to supply power to the payload. I have a signal ground, and then I have 2 signals coming from channels 5 and 6 output of the flight controller. I made this with an 8-position DuPont connector, so I have 3 additional empty positions for future expansion. If you're going to build projects like this, I recommend getting an assortment of DuPont connectors and the pins and sockets that go in them and the crimping tool. With all of the signal wiring completed, I mounted the antenna. I just put it on a zip tie and shrink wrapped it onto the zip tie just to hold the bottom in place. And then to cover all of this, I used my 3D printer to make a plastic cover that will slip over the antenna and cover all the wiring and give a nice, neat looking assembly. The cover is secured by the 4 remaining screws that attach to the 4 arms of the quadcopter, but I have a slot in the side so I can get to the USB connector on the flight controller to plug in a USB cable in order to modify settings without having to take this apart. With the CC3D flight controller, I'm using LibrePilot software, which you can download from librepilot.org, and there are many tutorials available online, so I'll just go through a quick setup procedure using the setup wizard. As it says, you must remove all propellers before proceeding. I have done so, and so we'll move ahead. I recommend doing a firmware upgrade, which I've already done, but use the upgrade in the wizard. In the next step, the software should correctly identify the board if you have plugged in a USB cable to the USB port on the board and to your computer. My radio receiver provides pulse width modulation outputs to control individual servos. It's the oldest and most common type of radio receiver, and so that's what I have selected for input configuration. My vehicle is a multi-rotor, so that default is correct. I'm using the most common Quadcopter X configuration, so the default is correct here too. My electronic speed controls that run the motors are capable of a fairly high refresh rate, so the rapid ESC is the right choice. But if you're not sure, a standard ESC will work with just about everything. It just isn't quite as responsive as the rapid ESC. One-shot ESC is more responsive yet, but it's disabled in my configuration. So here's the summary. We're ready to proceed. Next we'll calibrate the sensors, and I have the drone resting on a level surface, so I'll press the calculate button, and it will retrieve sensor data from the drone and then do a calibration, assuming that the surface is level. Next we'll calibrate the electronic speed controllers, and you have to confirm that all propellers are removed, that the vehicle is not powered by a battery yet, only by the USB cable, and that you've read and understood all of these instructions. So I'll check all the boxes and proceed. Once you press start, now you connect the battery. Again, make sure there are no propellers connected at this stage. Those tones are generated by the speed controllers. They actually use the motors as speakers to make tones. Once the tones stop, then disconnect the battery. Next we're going to calibrate the motors, and the motors are going to spin, so again, no propellers. I'm going to calibrate all 4 motors at once, so I'll check this checkbox. You have to reconnect the battery for this step, and then press start. And then move the slider up until all 4 motors rotate smoothly. You could tell from the sound that they rotated irregularly at a very low setting, and so I slid the slider up to, in my case, 1050 microseconds, where they all rotated smoothly. You want this as low as you can get while you still get smooth movement. You can choose a variety of performance tuning options to give better performance for certain kinds of airframes and so on. I'm going to scroll down and just select generic Quad X. You can find a lot of online tutorials on performance tuning for the flight controller to tune it to your liking so it is responsive as you want or stable as you want, but the generic Quad X is a fine place to start. At this point, we're ready to save the configuration, so just press the Save button. The controller needs to reboot at this point. Next, I'll run the transmitter setup wizard. At this step, the board is set to always disarmed so that the motors won't run during this process. I turned my transmitter on, so I'm ready to proceed. My radio transmitter fits the definition of normal transmitter for fixed wing or quad. I use mode 2 with the throttle and rudder on the left, elevator and ailerons on the right. Now I need to move each stick so it can identify the channels. I'm not going to use a flight mode switch, so I'll skip that step. I do have 2 accessory channels I'm going to use, and so I'll move my control knobs for those. And then I'll skip the steps for accessory 2 and 3. Then I center all the sticks and proceed, and then move all of the controls to maximum in all directions. This step seems to be broken in the software that I have. It should show movement of the sticks as I move them, but in fact it doesn't. I happen to know, though, from trying this once, that the pitch axis comes up inverted, and so I'm going to check the checkbox to invert the pitch axis. That completes the transmitter setup wizard. At this point, you need to press Save to save the settings to the board. The nominal front of the CCD board is identified with an arrow, and in my case I mounted it rotated 90 degrees so that that arrow points to the right of the craft instead. That's no problem, but I need to tell the software that I've mounted it that way, and so I'll do that by entering a -90 on the attitude page under the yaw setting, and that'll correct for it. Then I'll press the Save button. Once I've saved my -90 degree yaw offset, I need to recalibrate the sensors by pressing the Level button. And again, I'll press the Save button to save it. At this point, I'll switch to the Flight Data tab at the bottom to check the sensors. First, I'll pick up the rear end of the drone and verify that the artificial horizon raises as expected. Then I'll pick up the front of the drone, verify the opposite effect. Then pick up the right-hand side of the drone and the left-hand side of the drone. And then I'll turn it to the right and turn it to the left, and looks to me like all of the sensors are calibrated correctly. There's one last step I need to do on the input section on the arming settings tab. I need to change the arming settings from always disarmed to one of these options, and I choose the yaw right so that when the throttle is off and the yaw stick is moved all the way to the right, it will arm the quadcopter and allow the motors to start. Then I press Save and configuration will be done. I've completed the software installation and calibration, so I'm almost ready to go flying, but first I want to do a test of the drone without propellers to make sure everything is working as expected. And to start with, I need to power up the drone and arm it. So I'll set it on a level surface. That's important for this because the drone will not arm if it's not on a level surface. It's not going to allow flight if you're holding it when you try to arm it. And so to arm it, I'll switch my transmitter on, and then I configure the arming to be to move the left stick all the way to the bottom and to the right. And so that should arm the drone, and if I move the throttle up, then the motor should start. So far so good. You can check the throttle response, make sure that at a low setting the motors run smoothly, and then move it all the way to the top and make sure that it advances to high speed. So far so good. That sounds like it's working okay. This is the time also to check the rotation direction of the motors. Make absolutely certain they're turning the way they're supposed to be turning. I forgot to do that on one drone I built, and so the first time I tried to even take it off just a little bit, it flipped over. Not a big deal, but don't make that mistake. So make sure they're turning in the correct directions, and you'll also want to make sure you put the correct propellers on the correct motor so when they turn in that direction they push down. Again, easy mistake to do. So that looks good. I'm going to turn it on, and then I'll try operating the control stick. So with the motors turning at a low speed, if you operate the stick, the right-hand stick especially, you can also do it with the yaw control on the left stick, you'll hear the motors changing pitch. And you can just verify, just as a sanity check, for example, that if I move the right-hand stick forward That should increase the velocity, increase the speed of the rear motors. And you can hear it pretty easily. And the opposite is true if I pull the stick back. And then you can also try right to left. It's just a quick sanity check. I believe all the motors are operating correctly. They're rotating in the right directions. So I'm going to put the propellers on and try it out. Before mounting the propellers, I'm going to balance them to reduce vibration. And these little propeller balancers are quite cheap and easy to use. You just mount the propeller, and then if it's heavy on one side, remove a little bit of material on that side until it balances. I just use a hobby knife to carve a little bit off the tip of the heavier blade until it sits perfectly level. I completed the assembly and finished the software calibration, mounted the propellers, and now I'm ready to go flying. In the next video, I'll build a payload section with a better way to secure the battery, but for a test flight, I'm just going to secure it with tape. Okay, here we go. I didn't intend to take off quite that far, but I wanted to pop it up above the gravel. You don't want to fly it in ground effect too much because it's kind of unstable when it's real close to the ground. So offhand, hey, I'd say it flies pretty well. This is just a simple test flight, but seems pretty stable in the air. I'm hands off the right-hand stick, so it's flying nice and level. That's hands off right there. No hands on any stick, so got a nice stable flight. We'll try forward and back a little bit. Left, right, and then the yaw controls to turn. So I'd say we have a quadcopter. Time to land it. And again, it's a little unstable close to the ground, so I'll bring it down kind of close and then cut the throttle rather than risk dipping the props into the gravel here. Well, with a successful test flight, that concludes this part 2 video of the basic drone build. And it is basic. It flies. That's great. It doesn't do much else. It just flies. And you know, if that's all you want, you can build a drone like this. I would recommend at least putting in a battery voltage monitor. You don't want to run the battery voltage down too low because number one, the drone will fall out of the sky and probably get damaged. And number two, if you run the battery down too far, it can damage the battery and shorten its life. But I'm not going to do that because in the part 2 video, I'm going to build the payload section. And the payload section will have a stabilized video platform, a camera platform with a gimbal stabilizer for shooting aerial video. And it'll also have a first-person video transmitter to transmit live video back while I'm flying. And that will include an on-screen display that lets me monitor the battery voltage as well. So I hope you enjoyed this video. Stay tuned for part 3.